So, like we looked at rationalizability, we now look again from what a single player can say without knowing what others do, thinking what they can do, what they should do, and so on, but without knowing the true actions like we had in Nash equilibrium. And first we consider what a player surely will not play. So we exclude those which are never best responses iteratively. So we exclude something which is never best response. Then in the obtained game, we already see what is not a best response, and so on and so forth. So we show that actually this iterative exclusion of never best responses is equivalent to rationalizability. So first, a definition: a pure strategy is never a best response if it's not a best response to any belief about others of the agent I. Now, by definition of rationalizability, of course, never a best response is not rationalizable. Now, a strategy is never a best response if and only if it is strictly dominated. Well, being strictly dominated is probably never a best response. It's clearly because it's strictly worse than someone else. But the other way, the other direction is not clear. And anyway, we are going to prove both directions now. So being strictly dominated in the mixed sense, like we already, is the same as saying that someone is never a best response. And I'm going now back. As I said, we are going to iteratively delete never best responses. So we are going to iteratively delete strictly dominated strategy and show that this is equivalent to rationalizability. So it's nice that this may be reasonable but definitely non-intuitive, not immediate result holds, that iteratively deleting strictly dominated strategies is equivalent to eventually arriving at rationalizable strategies. So the proof is as follows. One important remark is that the strict domination can be defined without defining mixed strategies. It seems that, the strict domination in the mixed sense, which originally is defined using the mixed strategies. I remind that in the beginning I defined strict domination only by a pure strategy, and then I extended it to mixed strategies. And strict domination can be defined in some other way by saying that someone is never a best response. It means that even if mixed strategies are somehow not acceptable because we say it's not realistic that people will mix whatever, because it's not even a scientific, it's more like a philosophical discussion, or at least a psychological discussion anyway, whether mixed strategies are realistic. But even if they're not acceptable, we can talk about being not a never a best response, and therefore deleting strictly dominated strategies can be seen as deleted never best responses. So it can be justified. So this lemma gives this stronger, steady basis to deleting strictly dominated strategies and to the mere notion of strictly dominated strategies. That it will not be played. So how do I prove that? Actually, that proof is some other proof is a very nice thing to see as a tool, as an idea to prove. And the proof is as follows. By the way, it's not the only proof, but it's a short proof relative to another proof I once saw. So this proof is at least from the book by Osborne and Rubinstein, as I said, most or even maybe all the lesson today. So consider a game and consider some strategy SI star. And now we define another game, which unlike the first one, which can be any which can be any strategic game. The new game G prime has only 2 players. Now the first player has strategies which are all the strategies of player I. The player S prime eyes, S star eyes, of whom we looked at. Besides, aha, 1 second. I think yes. My apologies for the confusion. So consider any strategy S star I of player I. Now define a new game G prime where it has 2 players only, and the strategy of the first player in this game is defined to be the strategy of player I in the original game minus S star I. We don't know anything about S star I, just a strategy, a pure strategy. Now the strategies of the second player are all the sub-profiles of players other than I, S minus I. Now the utility of player I is defined to be the utility of player I when the first player plays Si, something from S prime 1, and the second player plays some S minus I from S prime 2. The utility of Si, of U prime I, the U prime I function, the utility of player I, if that is the strategy profile, is defined to be the utility of player I in the original game if player I plays Si and the other plays A minus Y. So it's defined by what the original game gives player I. Minus what player I would get if she played S star I instead of Si. And S star I is some strategy we fixed at Si. And the utility of the second player is defined to be just a minus of the utility of the first player. So it's a zero-sum game on 2 players. That's how we define it. So now let us continue. The first paragraph is just copied. And now we continue from here. So S star, now we have a chain of equivalences which begin with S star being never best response and ending with S star strictly dominated. And since these are equivalences, then we eventually will prove that this is the same. So S star I is never a best response. I apologize for writing this not in a column, one below another one, but just like that. I wanted to fit them all in one slide. So S star is never a best response. It means that for any strategy of the other players, there is some one for player I which is better. But the strategy of other players in the original game can be said the strategy of the second player in the G star game by the definition of G star and this. So if I have a strategy of the second player, there is someone who is better than the star I, strictly better. So there is someone at player I, and by definition of S prime I, you can say that Si is in S prime I. Which is strictly better. So by definition of U prime, we can say that U capital, because it's mixed extension already, of Si, which is strictly better than S. Okay, I apologize. apologize. So let me make it slower. S star I is never a best response means that there is someone such that there is some Si which is strictly better. It means that this UI of that someone will be better with Si than with S star I. And if there is such a P, it means that aha. Yes, exactly. So this I just, so there is someone which is strictly better. Now that holds if and only if the best, the minimum value of this U star I, U prime I, when I allow Si to be chosen anyhow, is positive. Forget the minimum. Forget this. Forget this. Look only at the maximum over U prime I, prime 1. We said that for any P2, in particular for this P2, there exists Si such that this will be positive. So the maximum also will be positive over all Si in S prime I1. Now since it's for any P2, it's also positive if I take minimum over those P. From compactness, we have a minimum. Compactness and continuity because of its of linearity. Okay. Now from the linearity, we can replace the maximum over prime pure strategies given some P2 by maximizing over the mixed strategies. Now the minimum over P2 of the maximum over P1 is the same as the maximum over P1 of the minimum over P2, because it's a mixed extension of a zero-sum game. We built G prime to be a zero-sum game. So we built it a zero-sum game. In the mixed extension, there exists a Nash equilibrium, a mixed Nash equilibrium, a Nash equilibrium to the mixed extension. And it means that min over max equals to max over min. That's what we proved for zero-sum games. So min over max is positive and only if max over min is positive. Now, what does it mean that max over min is positive? It means that maximum is positive. It means that there exists some P star 1 such that the minimum is positive, so that any P2 gives us something positive. So there exists P star 1 such that now we're going back to the original game. U1 of P minus I P star 1 minus UI of P minus I P star 1 minus UI of P minus I S star 1 is positive, because that's the definition of U prime. I remind that's the definition. And then we simply look at this linear extension because of the mixed extension. Now, so we've proven that there exists P star such that for any P minus I, UI of P minus I P star will be strictly larger than UI of P minus R S star 1. So there exists some strategy of the other players, because S prime 1. Aha, my apologies. There is this strategy of player 1 other than S star 1 by the definition of S prime 1. Such that for any strategy of the other players, it gives a strictly better result than S star 1. So S star 1 is strictly dominated, the same. And as I said, we start with the assumption that S star 1 is never a best response and ended with being strictly dominated. So being never a best response is equivalent to being strictly dominated. Now, having proven this interesting lemma, let us talk about iterated elimination of dominant strategies, or in the case of strictly dominant strategies, iterated elimination of strategies who are never a best response, because the lemma says it's the same. So that was already something which we saw, an iterated elimination of strictly or weakly dominant strategies. The definition is general, but we are going to work with strictly dominant strategies here. So iterated elimination of a game is a shrinking sequence, so a sequence which is strictly small at every point, strictly included, such that at any point t, the strategies which are removed are weakly, strictly depends on whether we are talking about iterated elimination of strictly or weakly dominated strategies. So they are strictly or weakly dominated in the restricted game. Restricted to the S at t minus 1. So at any point, we look what are the strictly or weakly dominant strategies, and at least one of them we remove. Not necessarily all of them, we are free, but we remove at least one of them, so that we have a shrinking sequence. And if at the end, at time period t, no strategy is strictly or weakly dominated, then the sequence is maximal. Now here we assume that the sequence is maximal unless we say otherwise, and in that case, the strategies in the end of this maximal sequence are set to survive the iterated elimination of strictly or weakly dominated strategies. So the strategies of this process, at the end of this process, when we cannot remove any strategy because there is no strategy which is strictly, now let us talk about strictly dominant. Okay, sorry. It's too general. So the strategies at the end, which cannot be removed, they are called to survive iterated elimination of strictly or weakly dominant strategies. So those strategies who are those strategies which survive strictly or weakly dominant strategies. Now, let us now talk about iterated elimination of strictly dominant strategies. And unless we say we are going to talk at this lesson only about iterated elimination of strictly dominant strategies. Now, example. So this is a game. Also, it's example from Osborne and Rubinstein. Here, B is strictly dominated by the combination of half t, half top plus half middle. Because here, half of 3 plus 0, 1 half, it's larger than 1. The same here. Half of 0 plus half 3 is 1 half, larger than 1, so B can be removed. Now here L is strictly dominated by R. Now before we deleted B, L was not strictly dominated by 1 because 1 is larger than 0, but after deleting B, L can be deleted because it's strictly dominated by 1, and we get the following. And now T is strictly dominated by M because of 0 is smaller than 3, and we are left with only one possible strategy profile, middle right. So that's the only strategy profile which survives iterative elimination of strictly dominant strategies, or by the lemma, iterative elimination of strategies which are never best response. And now we are proving the following remarkable theorem. In the book, it's called a proposition, but I think it's important, and it can be called a theorem. Even if it's not very complicated to prove, I like to call it a theorem that connects iterative elimination of strictly dominant strategies with rationalizability, which we began with. And the theorem is as follows. In a finite game, let X to be the step strategy profile which survive iterative elimination of strictly dominant strategies. Then, for any player, xj is exactly the set of j's rationalizable strategies. So the rationalizable strategies, as we defined in using two equivalent definitions, are exactly those who survive iterative elimination of strictly, I emphasize strictly, dominant strategies. And the proof is as follows. So one direction is simple. Assume, actually they're both not very hard, but a bit confusing perhaps. So let Si be rationalizable, supported by Zj's in the second definition of rationalizability. For any T in this case, it's not a nesting stage in the first definition of rationalizability. No, we look here at the second definition. But T here is a stage at iterative elimination of strictly dominant strategies. I remind you that's the definition. So for any T, Zj, the strategies in this definition which support the rationalizable strategies actually have to be in ST, since every strategy Z is a best response to the others. So it will not be deleted, and then the others will not be deleted, and so on and so forth. In particular, and being the best response, it's not strictly dominated, so it will not be deleted. Formally, it's by induction. So this set Zj has to remain in any step of deletion of this iterative deletion of strictly dominant strategies, and therefore it also survives the whole process. Okay, that's one direction. Now conversely, let us look at something which survives the whole process and at some player, right, and show that any strategy which survives the whole process, xj, right, that's the definition, xj's are those who survive the iterative elimination of strictly dominant strategies, that all of them are rationalizable. So first, no strategy xj is strictly dominated in this final set of strategies which survives the iterative deletion elimination of strictly dominant strategies by definition. So what does it mean that nobody is strictly dominated? It means that any strategy in Sj, for any candidate to dominate that, there is a setting of what others do, there is a belief on what others, such that Sj is the best. It's not strictly dominated. Okay, my apologies. I'm confused. I'm confused now from scratch. So let us look at some play and let us show that every strategy in XJ in the set of your strategies which survive iterated elimination of strictly dominant strategies, that every such strategy is also rationalizable. So no strategy in that J is strictly dominated by others in this game when we look only at SJs, because we assume that it survives the determination of strictly dominant strategies. Nobody is already strictly dominated. So what it means is that any strategy in SJ okay, so typo fix. There was a typo in the slide, so no strategy in XJ is strictly dominant in the game which has only XJs, because we assume that those are exactly XJs, are exactly those who survive iterated elimination of strictly dominant strategies. And that means that for any one in XJ, there is a belief about the other such that that is a best response. So being not strictly dominated, it means that it can be a best response. Remember the lemma: never best response if and only if strictly dominated. Not strictly dominated if and only if can be a best response. So here it can be a best response. Now among xj's, now is it a best response among sj's? Now assume that sj in xj is a best response among xj's but not among sj's. Then it means that there is some t such that sj was a best response among tj, but not before we removed something, not among st minus 1j. So there is a bj that has been removed that was a best response among st minus 1j, but it would be contrary to elimination of bj, because we don't remove best responses, because we remove iteratively eliminate strictly dominant strategies, therefore not best responses. So therefore sj has to be also the best response among sj's, so taking something which is which survives iterated elimination, we prove that it's the best response among xj's to something, to some belief about x minus j, and thereby we've proven that that's rationalizable. And thereby we've finished the proof that surviving iterated elimination of strictly dominant strategies is the same as being rationalizable. One immediate conclusion is the set of strategies which survive iterated elimination of strictly dominant strategies is independent of the elimination order, because the theorem does not assume any elimination order. We prove that this set which survives this iterated elimination of strictly dominant strategies is always equal to the rationalizable strategies. So this set is independent of the order. And now let us consider recall the example that we wanted to find the rationalizable strategies, and we started by deleting strategies which were strictly dominant. And at some point we said, yeah, we cannot delete anymore, so we needed to prove that all those are already rationalizable. But now we say that we can just stop. Once we know that nobody is strictly dominated, so that these all survive exactly the set of strategies who survive the iterated elimination of strictly dominant strategies. That means that they are all exactly the rationalizable strategies. And the last, I think, important example or remark is that the definition of belief that I said we allow for belief to have dependency among what others do. Without that, if we did require independency, then neither the lemma that never being a best response is equivalent to being strictly dominated, nor the theorem that surviving iterated elimination of strictly dominated is equivalent to being rationalizable hold. And we can just prove that, or show an example, that they both the lemma and the theorem, which are main results here, would stop holding if the definition of rationalizability required a belief to only believe in independent actions of the opposite players, like in mixed strategies. And the example is as follows. So the example has three players. The same example we saw once, that one plays chooses the row, two chooses the column, and three chooses the table. And they're identical pairs, they're identical, and they're written in the table. So here, M2 is the best response. Then we know that there's probability half up or low is played, and probability half down right is played. Because M1 would give us like half of 8, 4. M2 gives us half of 4 plus half of 4. 4. M3 gives us half of 8. 4. And M4 gives half of 3 plus half of 3. 3. So M2 is one of the best responses. Not the unique one, but one of the best responses. And therefore, by the lemma, being a best response, it's not strictly dominant. Now, M2, however, is not a best response, as we already saw. I remind the inequality that it could not satisfy is not a best response to any independent mixed strategies. And thus, under the modified definition, which required independent mixed strategies in the belief, it would not be rationalizable, because a rationalizable thing has to be a best response. So, if we required the beliefs to assume independence, it would be not rationalizable, but it would not be strictly dominated. So let me say, okay. So first of all, the lemma would be contradicted in this case, because it would not be strictly dominated, which the lemma says means that it has to sometimes be a best response, but it also is not a best response, ever, if we require this independence. Now the theorem is also contradicted, because my apologies, second year. The theorem is contradicted because it's not rationalizable, therefore by definition it would not survive iterated elimination of strictly dominated strategies. It would not survive if the theorem held. I repeat, it's not rationalizable. Therefore, if a theorem held, it would not survive iterated elimination of strictly dominant strategies. But since it's not strictly dominated, okay. My apologies for the delay. So basically, we need to prove or to exemplify that the lemma theorem can be wrong if the belief has to assume independence of self. So we prove that in this example, M2 is a best response in the sense we look at to this belief which is dependent, and therefore from the lemma we know that it's not strictly dominated. Now another thing is that, let me see whether we already have, okay, let's just continue. So however, M2 is not a best response to any independent mixed strategies. That inequality we already saw. And being not a best response, it cannot be rationalizable under these modified definitions, when belief has to look to only believe in something which others are independent. Now let us look why this example actually why it defies both lemma and theorem. So under new definition, this is not strictly dominated. So the lemma would then imply that it's sometimes a best response, but it's never also a best response. So the lemma fails. Now as for theorem, is that it's not rationalizable under the modified definition. And under the original definition, it was rationalizable. So if the theorem held under the modified definition as well, then we would say that it has to survive iterated elimination because of the original definition, the theorem, but in the new definition, if the theorem held, it would say that it cannot survive iterated elimination of strictly dominant strategies. But the iterated elimination of strictly dominant strategies does not depend on this difference in how we look, in which beliefs we allow in the definition of rationalizability. So there is a contradiction to the theorem too. So neither element of the theorem holds in general when we require that belief assumes that the others are independent. And the last part is a very yes, it's something we already saw, that just I remind you, unlike the strong strategies, strong dominant strategies, which those who survive the iterated elimination of strictly dominant strategies don't depend on the order whom, when. If you talk about weakly dominant strategies, then here those who survive depend on the order. So that's yet another reason why it's not used, in addition to other reasons, like that we can lose Nash equilibrium, for example. So being weakly but not strictly dominant has less reasons to eliminate, because there may be other best responses to belief. But here, in addition, as I said, the set of those who survive this iterated elimination can depend on the order. For example, and again, this example is from Osborne and Rubinstein, if first eliminate top, which is dominated by weakly dominated by middle, and then L is weakly dominated by R, that's what we are left with. So 2 1 2 1, those are the profits, and the strategies are M, middle and bottom for the column play, row play, and the right for the column play. Now, on the other hand, if we start with eliminating the bottom, which is weakly dominated by middle, for example, and then we eliminate the weakly dominated R, then we are left with strategies top and middle and R, and then profits are different from what we had. So it was 2 and 1, now it's 1 and 1. Okay. So we saw this nice idea of rationalizability, which has more realistic, weaker than Nash equilibrium epistemic assumptions. We saw some qualities of that. We proved that surviving iterative elimination of strictly dominant strategies is equivalent to rationalizability, and some other properties.